All right, guys. Hopefully, you are well. We're gonna flip this around a little bit. We're going to do a flipped classroom kind of approach for 15.3, which is double integrals in polar coordinates. It's so visual that I think it's going to be better for me to actually just make a video so that you guys can see it as clear as possible versus over Zoom. I'll miss the interaction for sure, as you'll figure out. Like me teaching a camera just doesn't work. But this first video is going to be pre-calculus. So this is stuff you saw in pre-calculus related to polar coordinates, and we're not covering all of polar coordinates. I'm just going to do a brief refresh of the kind of stuff that we'll need in section 15.3. So this first video is the pre-calculus of polar coordinates. And the word polar, I think, really comes back to the globe, where we think about the North Pole and the South Pole. And if you think about looking at a globe and how it's all divided up, you know, where you're looking at those lines, that's kind of where I think the idea of polar comes in. Angular. So we're so used to, and we're so comfortable after being taught for so many years with our Cartesian coordinate system that, you know, if we have X and Y, and if we go back to 7th grade when we were first really learning about this, you know, you pick any point in the Cartesian plane, you can describe to somebody how to reach that point, you know, by just saying you go over some distance, like, for example, maybe let's just say this is 5. You go up some distance y, we'll just call that 3, and then we can think of this as being the point 5, 3. You know, you go over this distance and you go up that distance. And as long as what we're describing and what we're interested in, you know, has the shape of something that looks like a rectangle, or we can use the idea of the rectangle, this works out fantastic. And we don't think about things like this, but when we really talk about like the line x equals 2, remember how hard that concept was when you were in when you were in Algebra 1. You're like, how can that be a line? What they're refusing to write is that y is allowed to be, y is allowed to do whatever it wants. So if we look at all the points where x is 2, if we look at all the points of x equals 2 and let y run from 0 to infinity and from 0 to minus infinity, we get a line that looks like this. We get a line that looks like this. And similarly, like for example, if we say y is equal to 4, that ends up being a horizontal line, and it confuses kids because you're like, it's y. Why isn't it up and down? Well, it's because x is allowed to do whatever it wants. So like, for example, if here's 4, you know, and we're always going to keep that x coordinate at 4, then if we're looking at x going between minus infinity and infinity, we get this line. As we go from 0 to infinity and from 0 to minus infinity, we get that line there. And again, like if we were thinking about our type 1 regions, we're really exploiting the fact that, like, for example, here's A, here's B. This is like my f of x, and this is like my g of x. But we're really using the fact that x is going between A and B, and then my y can run between there and there. And similarly, with a type 2 region, we're just flipping it over. However, there are geometries where the Cartesian coordinate system just is not the best coordinate system to work in. And the next simplest coordinate system is what we would call our polar coordinates, which is what we call our polar coordinates. You can almost think of them as being like circular coordinates, okay? And so I want to introduce, well, I mean, you saw it in pre-calc, but it may have been a while since you've seen it. If I'm thinking about like using a polar coordinate, the way that works off of, it works from trigonometry. And I just want to review a little bit here. Like if you've got a radius and an angle, okay, and we're thinking about trig, then we can go back and we've got our opposite side and our adjacent side. I know you call this the hypotenuse, but I want to call it the radius because that's where we're heading. This is my angle, my radian angle. Now let's go back and remember, okay? So if this is r and this is theta, what do you got in your gray matter for a trigonometric expression for the opposite side? No, and I'm hearing nothing because I'm teaching a camera, okay? But I'm believing somebody saying, oh, Dr. Warren, the opposite side is the opposite side. Well, I don't remember that, Dr. Warren, but I do remember that the sine of theta is the opposite over the hypotenuse, and then just doing like some simple algebra, then the opposite is the hypotenuse, which is in this case r, times the sine of theta, because this would be r, and then I know it's just pretty simple, multiply both sides by, so that we would get that the opposite side is r times the sine of theta, and then you remember also the cosine of theta is the adjacent over the hypotenuse. And that would lead to our adjacent side being r times the cosine of theta. Okay, so I've got this right angle here. This side is r times the sine of theta, and this side is r times the cosine of theta. And then if I did tangent of theta, that's my opposite side. That's my opposite side. Over my adjacent side, and you can see here, my opposite side is r times the sine of theta. My adjacent side is r times the cosine of theta. These cancel, and then we do get the relationship that we would have for tangent. Now, like Dr. Warren, how does this describe a new coordinate system for me? Well, I can look at this point 5, 3, and I can also describe it by a radius starting at the origin and going up to here, and an angular measurement, theta, in radians from the x-axis. Now, it's not too hard to get this. My radius, if you just drop straight down, my radius, well, this is 5, this is 3. Look at the triangle. This is the hypotenuse. My radius is, using the Pythagorean theorem, a squared plus b squared equals c squared. Or I get that my r squared would be equal to 5 squared plus 3 squared, or that r is equal to the square root of 5 squared plus 3 squared. And then we can actually find our angle theta because my opposite side is 3 and my adjacent side is 5, that my tangent of theta would be equal to my opposite over my adjacent, or the angle would be the arctan or tan inverse of 3/5. So you give me any coordinate in Cartesian form, like for example 5, 3, we can find the corresponding polar form by just doing calculations that are very similar to this. Now you're like, well, Dr. Warren, why are polar coordinates at all anything of any interest to us? It's because so much of what we see in nature, especially celestially, deals with things that are circular. And so, like, for example, if we have a domain that's a circle, it seems a little stupid to use rectangles when there might be a better coordinate system to describe a circle. Okay, and so this leads us to the idea of polar coordinates. Because in polar coordinates, what we have is that, like for example, suppose this is, remember our equation of our circle, x squared plus y squared equals 7 squared. So this would be a circle of radius 7. That if I'm thinking about this in terms of my my Cartesian coordinate system, well, this would mean that y is equal to plus or minus the square root of 7 squared minus x squared. It's definitely not a function as far as x is concerned, but I can think of this as two functions. The top part is the plus 49 minus x squared. The bottom part is minus 49 minus x squared. Okay, and so if you're thinking about this as a type 1 region, which is where we're heading, if we're thinking about this as a type 1 region, we're saying, well, that as x goes between -7 and 7, my y is going to run between minus the square root of 49 minus x. This bottom part is like my f of x, and the upper part is like my g of x. But integrating things with square roots, we found in 236, is quite complicated. Okay, so the question is, does polar coordinates, when we have geometries that look circular, make our lives better? And the answer is often yes. Let alone if we have geometries that are parts of circles. Like if we have a tire, and we're only going to be concerned with part of an annulus of a tire, then suddenly this is far harder to represent in Cartesian form. So there's some motivation. And now let's just get into the nuts and bolts of polar coordinates. Okay, and so that's what we're going to do right now. So let me erase some of this. You can probably just scroll through this as I erase. Now we'll come in here and we'll give ourselves our Cartesian plane. We're not going to leave that. This is going to be x and y, but now we're going to be thinking about polar coordinates. Okay, so what we can do is we can think about theta as being an angle that starts here and moves that way. And as theta goes positively, we keep spinning around the circle. And as theta goes negatively, we keep spinning around the circle. My radius is going to be, my radial coordinate is going to run like this for a given angle theta. Okay, and then it goes this way if I'm thinking about r is running between minus infinity to infinity. So I can think of theta as going between minus infinity to infinity, and I can also think about r as running between minus infinity to infinity. Now the thing is, unlike the Cartesian system, where we can hit every single point in the Cartesian plane as x goes between minus infinity and y and infinity, and y goes between minus infinity and infinity, because theta keeps spinning around and r goes here, we don't actually need all of the angles to fill up our Cartesian plane. We just need some region, and we can hit all of our angles, which is different than Cartesian systems. But we're not going to go into those subtleties. Again, that's more kind of what we would do in PreCalc. Okay, so let's imagine now where we're describing a region in polar coordinates, and I want to show you how much simpler it is than for circular kind of things than Cartesian coordinates. Like for example, I could say let my radial coordinate run between 0 and 2. So my radial coordinate's going to run between 0 and 2, and typically this is we mark this as our first component in our ordered pair. Now look at me and listen. This is not x. This is not x. This is a polar coordinate. This is not xy. This is not the ordered pair xy. It's an ordered pair that describes a point in the plane in polar coordinates. Theta is my angular coordinate. And we're going to look at all the points in polar form where theta runs between, let's just say, r is going to run between 0 and 2. And let's just say theta is going to run between 0 and pi over 2. And try to see what that region would look like. Try to see what that region would look like. Well, if I'm allowing my radius to run between 0 and let's just say that's 2, and we're allowing theta to go between 0 and pi over 2, so this would be like 2. This would be like 2. You give me any point inside this quarter circle, there's going to be a radius that's definitely less than 2 and bigger than 0, and an angle, theta, we'll just call this R1, theta 1, that would hit that point. Now again, describing this kind of a region in Cartesian form is a nightmare comparatively. We're just saying, okay, in polar form, r is going to run between 0 and 2, and theta is going to run between 0, and pi over 2. And the way we would write this is much like we would with our set notation. We would say, let D equal all the ordered pairs. But now, guys, these are polar pairs, r theta, such that r is running between 0 and 2, and theta is running between 0 and pi over 2. And hopefully, now you're like, well, Dr. Warren, do something more fun. Okay, so that's not really what you want. You just want the semester to end. But I'm going to pretend like you said, oh, Dr. Warren, this is so much fun. Do something more fun. Well, let's just say now that we change this and we say, okay, we don't want it to run from 0 to 2. We want it to run from 1 to 2. And let's try to think about what that region would look like. So now you try to draw the new domain where r is no longer running between 0 and 2. Now it's running between 1 and 2. And we'll have our second coordinate, in our polar coordinates, theta, run between 0 and pi over 2. You go draw that. Pause me and you go draw that. Okay, and hopefully what you said when you unpause me is that we're still letting our angular coordinate run between 0 and pi over 2. So we're still going to be sweeping out in this first quadrant, but now r is going to go from, we're going to have nothing between 0 and 1, but r is now running between 1 and 2. R is now running between 1 and 2. Okay, so now I'm going to draw another domain. I'm going to list another domain, and I want you guys to try to draw what we're talking about in our Cartesian plane. So imagine that my domain in polar coordinates is all the points, ordered pairs, r theta, not xy. These are not Cartesian coordinates, where r is running between 2 and 4, and theta is running between pi over 4 and 3 pi over 4. So my angular variable is running between pi over 4 and 3 pi over 4. And my radial variable is running between 2 and 4. You give yourself a new xy and go try to draw that domain. Pause me and go try to draw that domain. And again, this is all pre-calculus. And again, this is all pre-calculus. Okay, so hopefully you've unpaused me. Okay, so we've got our classic Cartesian coordinate system. And now what I want to do is I want to try to draw this domain. Well, my angular variables are running between pi over 4 and 3 pi over 4. So now let's have a little fun. And I know we don't really mean that. Let's have a little fun. If we're thinking about theta equals pi over 4, we can actually think of this as a curve in our Cartesian coordinate system. You're like, no, Dr. Warren, let's not do that. In the same way that we can think about x equals 2 as being a line in our coordinate system. If we're thinking about the Cartesian line, x equals 2, we're saying that we're thinking about all the ordered pairs, Cartesian pairs, where x is 2 and y is allowed to do whatever it wants, which goes like this. In the same way, I can think about theta equals pi over 4 as being a coordinate curve, where I'm fixing the angle theta to always be pi over 4, but allowing the radius to do whatever it wants. Now, typically, what we're going to be doing in this class, we're not going to worry about r being negative. We're just going to think about r being positive. So we're thinking about, here's pi over 4. This angle is pi over 4, and we're going to let r do whatever it wants, which is going to give me this coordinate curve. So this is actually the coordinate curve theta equals pi over 4. You're like, Dr. Warren, damn it, why are you calling it a curve? It's clearly a line. And in fact, it's like a line, if we're thinking about it, it's like a line back in Cartesian form of y equals m over x. But in polar form, it's just theta equals a constant. Now, if we're thinking about theta equals 3 pi over 4, well, we're past pi over 2. And so this would actually be the coordinate curve theta equals 3 pi over 4. So my theta is running between here and here. My radial variable is running between r equals 2 and r equals 4. Now you're going to be angry, but we can think of this as also being a coordinate curve where, for example, where we have r equals 2, we're fixing that and we're allowing theta to do whatever it wants. And so if I'm thinking about that as being my coordinate curve, unlike y equals a constant, which gives me a horizontal line, r equals a constant fixes the radius out 2 and lets theta do whatever it wants. And so this would be like the coordinate curve, and now you see why I'm calling it a curve, r equals 2. And similarly, I don't think I'm going to be drawing this real well. This would be the coordinate curve r equals 4, where theta is allowed to do whatever it wants. Where theta is allowed to do whatever it wants. And so if we're thinking about the region that we'd be interested in, it would be that region right there. It would be that region right there. So I'm hoping this is making sense. I'm hoping this is making sense because now we're going to do something that's probably not going to make a lot of sense. Now, oh, thanks, Dr. Warren. That's exactly what I want to hear. What about functions and polar coordinates? You're like, Dr. Warren, damn it, I can barely understand polar coordinates right now. Okay, so then we'll hold off on functions of polar coordinates. How can I go Dr. Wood, where are you going? Okay, I'm gonna ask this question. Suppose that I'm given something in Cartesian coordinates that would be better off in polar coordinates. How could I go from Cartesian to polar? Or suppose I flip it around 180 and say, I'm given something in polar coordinates that really would be much better in rectangular coordinates, Cartesian coordinates. How do I go between the two? Okay, and so that's what we're going to end this brief introduction. Well, not introduction, a little refresher of polar coordinates. Okay, so let's just say, how do you go between the two? So that's what we're going to do. Let me erase again. You may want to pause and just move ahead until you see some drawing, just to save yourself time. So let's imagine that we want to go between our two coordinate systems. Well, I've got a point here. I've got an arbitrary point in my xy plane, and let's just mark it like we're most comfortable with in Cartesian form, xy. Like Dr. Warren, I love this because like if this is 7 and this is 5, this makes sense. I go over 7, I go up 5. I get the Cartesian lines. X equals 7 is this, y equals 5 is that. Now you're telling me there's another ordered pair, and this ordered pair has nothing, does not mean go over and go up. That's r theta, where this is describing a radius, and this is describing an angle, and this is still the same stinking point in the xy plane. Yes. How do I go between the two? Well, let's draw in our angular, our polar coordinates. So we've got this radius whose length is r, and we've got this angle which is theta, and we've got our Cartesian form where we have x being a constant, and then we've got y being a constant, but I'm going to work with this part right here. And what we see is this right triangle. And it's from this right triangle that we end up, and we looked at this a little bit, but I didn't write it down specifically. If we look here, the opposite side is the hypotenuse times the sine of the angle. So this would be like our sine theta. And this side is our cosine theta. And so what we see is that the x coordinate written in polar form can be just described by x equals r times the cosine of theta, which allows me to convert Cartesian x into my polar coordinates. Similarly, my y, which would be going up, is r times the sine of theta. And so this is a conversion that allows me to go, from my Cartesian coordinates and converting a function into a function of my polar coordinates. Now, what if I want to go the other direction, where I'm given a radius and an angle theta, and I want to get an x and a y? Well, you can see here, right here, you can easily go between the two. Now, what if you're given a Cartesian point and you want to find the radius and you want to find the angle? Well, again, we could do what we were doing before. If x is equal to r cosine of theta and y is equal to r sine of theta, then this distance is x, this distance is y, this guy is equal to this, and then we would see that x squared plus y squared, just Pythagorean theorem, x squared plus y squared is r squared, or r is equal to the square root of x squared plus y squared, if we're just thinking of letting r go between 0 and infinity. And then if I look at x over y, sorry, y over x, then I've got r, and again we did this already once, r sine of theta over r cosine of theta, but it's probably worth doing again. These cancel, and we get that this is equal to sine of theta over cosine of theta, or just tangent, and so that we can see that theta is equal to the tan inverse of y over x. So if you're given an xy and you want to figure out the corresponding r theta, well, you just use square the x coordinate, square the y coordinate, take the square root, do y over x, okay, and do tan inverse, and that'll give you your angle theta. I'm hoping this brief refresher helps you out. If you're not too familiar or you don't remember too much from PreCalc, and there's a lot more to polar coordinates. But not that what we need to do integration. All right, thanks. Hope this helps.